Okay. Thank you for everyone for attending my online student PD reading seminar. And today we have Minh, currently a PhD student at Michigan State University. He's going to talk about blow-up prevention in some chemotaxis models. Please, Minh.
Okay, thank you very much for your nice introduction. Thank you everyone for attending. Today I would like to talk about blow-up prevention in some chemotaxis model. Right, so we will go over four sessions: the introduction, some known result, and the main result, and finally, if we have time, we go to the sketch of the proof. First of all, what is chemotaxis? Chemotaxis is the phenomenon which deprives the cell secrete chemical signal substance, and the cell particularly orient their movement toward increasing signal concentration. And chemotactic movement plays a key role in many processes of communication between cells. For example, formation of aggregate, such as aggregation of slave mode, is the video that I show you at the beginning, and in tumor migration, and in organization of cell position during embryonic development, and so on. So that is those are the application in biology. So how about mathematics? So one of the first model was introduced and studied by Keller and Siegel in 1970. Here, the function U standing for the density of population, and V the concentration of signal. And the PDEs here describe the density and the concentration of signal. So this is the first equation is a nonlinear parabolic equation. Fu is the source, and so this is the diffusion term, and this is the reaction term. And Vt, so the second equation is parabolic when tau is positive, and elliptic when tau is 0. When tau is 0, we call parabolic elliptic system. When tau is 1 or bigger than 0, then we call the fully parabolic system. We will deal with the open bounded domain with smooth boundary and non-negative initial data. And we also need the homogeneous vanishing Newman boundary condition. Right, so this is one of the most simplified version of chemotaxis. And this has some nice property. One of the well-known property we call the critical mass phenomenon. So this equation nicely captures that property, but this equation is not chemotaxis. Is come from physics, the interaction of particle, and the domain we consider is the whole R2. So it has some nice property. So let's see. So the first property, if we assume some decay property for the solution, then we can easily see the mass conservation property. We take derivative of this, and it's equal to 0. And next is the second momentum identity. If we set M equal to the L1 norm of U, and we differentiate this second momentum, we're going to get this identity. And this equation can be easily seen from the following. We just we differentiate and we make use of the first equation. After that, we use integration by parts, and then we use the fundamental solution for Laplace equation. We plug in, and finally we use the symmetric property of this integral, so it's equal to a half of x minus y. So this is cancel out. So we have m squared divided by 2 pi here. So in other words, we have this equation. So this is the linear equation. So if the second momentum is finite, then we have the following. When m bigger than a pi, then the second term of the right hand side is negative, right? So when if we assume solution exists globally, then time goes to infinity leads to a contradiction. The left hand side is non-negative, the right hand side is negative, so it's a contradiction. So U cannot exist globally. It must blow up at some point. And when the mass equal to a pi, then this one is cancelled, and we have the second momentum is reserved in time. When mass less than a pi, then it behaves like a heat equation. The second momentum grows linearly in time while the mass is reserved. Right. So now we return to smooth battery domain. So do we have the similar critical mass phenomenon as in the equation that I just right here? Okay. So so here is some well-known results. For example, in one-dimensional case, we consider f the source identically equal to 0, and in the open bounded domain. So in one-dimensional case, then Osaki and Yagi proved in 1997 that all solutions are bounded. So there's no blow-up solution for n equal to 1. For n equal to 2, then a group of 3 mathematicians, Nagai, Sanba, and Yoshida in 1997, they proved that if initial data and radio in X, then mass less than a pi, otherwise mass less than 4 pi. And this one for fully parabolic system. And if it's less than this critical number, then solution exists globally. So that is for the global boundedness part. And for the blow-up, finite time blow-up, we have some well-known paper here. For example, Jagger and Lucas in 1992 proved that there are many radial blow-up solutions when tau equals 0. And later, Nagai has the proof for non-radial blow-up solution in 2-dimensional case. This is for n equal to 2 and tau equal to 0. And in 1997, for the fully parabolic case, the 2 mathematicians here proved that there exists at least one radial blow-up solution. And then the result was later improved by Horstman and Wang in 2001, and find the exact value for critical mass 4 pi here for many non-radial blow-up solutions. So we have m equal to less than 4 pi, we have global existence. M bigger than 4 pi, we have blow-up. So 4 pi is critical mass for Keller-Segal in an open bounded domain, specifically in the unit ball for R2. But in higher than talking about analysis tool, then they all use Lyapunov functional and calculate the variation tool in order to establish the result here. And the number 4 pi is not cannot be easily seen from the analysis. It's not like this equation nightly capture the number 8 pi, but in the number 4 pi coming from the Schrödinger, the critical constant for Schrödinger Moser inequality, and because of that, then we have the number 4 pi here. Right. And in higher dimension, then we don't have many tools, and one of the first tool, maybe the first one to detect blow-up solution, it was discovered by Wingler in 2010. He proved that for any dimension bigger or equal to 3, and in the elliptic case, and there are many radial blow-up solutions. And he also showed the global existence part here. And for tau equal to 3 years later, then he modified and adapted the method, and it works highly for fully parabolic system. So that is the story for n bigger or equal to 3. We have a lot of open question in higher dimension.
Can I have a question, Minh?
Yes, sure.
So in the case n equals to 2, you say that if u naught and v naught are both radial, then 8 pi, if m less than 8 pi, then you have global boundedness solutions, right?
Yes.
Is it known that if m greater than 8 pi and u naught and v naught are radial, then things can blow up?
For that one, I don't know. Yeah, I don't know.
Okay.
So they constructed a non-radial blob solution, but for the counterpart of m bigger than a pi, whether they have constructed any blob solution. But of course, it will blow up for non-radial
Sure.
radial solutions, but for radial solution, then yeah.
Thank you.
Can I have also one follow-up question?
Yes.
So in the work of Herrero Velázquez, they construct one radial blow-up solution. Does anyone try to compute the mass? How big were the mass in their solution?
For that paper, they haven't shown that 4 pi the critical mass. They certainly have some number, but yeah. So for until 2001, then they find that the critical mass is bigger than 4 pi. For this paper, then they haven't done that. So yeah. So I am not sure whether they have shown any critical mass in the paper in 1997.
Yeah, you can go ahead, Minh, please.
Yeah. Okay, so when f here is identically equal to 0, then we know that a lot of results indicate blow up can happen, and there are many radial blob solution and non-radial blob solution. So if we add the logistic, we call this is the logistic damping, logistic sources. Then we have the minus mu u square here, and this term we call the quadratic degradation. Then we have some nice property because of the minus mu u square here. It may prevent blow up, and that intuition is true. For example, the paper in 2007 introduced that this logistic damping by Taylor and Wingler. They proved that the solution exists globally in elliptic case for any mu bigger than this certain number when n is bigger or equal to 2. So the solution is lexical when n sufficiently large. And then they also construct the meaning of which solutions in chemotaxis, and then they shows that which solution exists globally when mu bigger than 0 for n equal to 3. And later they improved that, Wingler, he improved that result for fully parabolic system. He found that when tau bigger than 0 and n bigger or equal to 3, and mu sufficiently large, but what exactly the value of mu? So that solution remained bounded was open question until 2016, right? And in 2015, Wang and Xiang improved the Born-like case for the paper in 2007. For 2007, we have mu bigger than this number. But what about mu equal to exactly this number? So that was proved by Wang and Xiang, when n bigger or equal to 3 and tau equal to 0. But the method they used is quite complicated, and later it was modified and improved by different methods. We have two papers in 2016 and 2017 prove that theorem, but use different methods. Right. And so now we go to some quantitative works. So here we see that mu is sufficiently large. But how large mu is? So we can go here. So first of all, the paper in 2015 concerned with that problem, but they consider for 3D chemotaxis fluid. So it involves Navier-Stokes equation in that, and it's not it doesn't belong to our interest today, so I didn't write the equation here, but it works for all the more general equation in chemotaxis. And 1 year later, Mu and Lin improved that result for mu bigger than 20 in the same system. Right now, we return to the chemotaxis. So Xiang, he found an explicit lower bound for mu when tau equal to 1 in 3, 4, and 5 dimensional case for chemotaxis system. And 2 years later, he improved the paper 2016 and find a smaller constant for mu in a general non-convex bounded domain. And in 2018, he also obtained some estimate for upper bound for U and V. So those are some quantitative work. And now, so we intuitionally we see that minus mu U square will help the estimate, but how do we see that the picture? And so we can look at the following analysis diagram. So if we make use of the second equation, we plug into the first equation, we have something like this. And so we can see that the last term can absorb nonlinear term, other nonlinear terms when mu is bigger than 1. So this term becomes negative, right? So when mu be big, it helps the equation in that sense. But when mu is less than 1, it cannot be seen by this equation. We have to have other way to see the problem. Right. So when mu is small, then we know that solution the global existence of which solution. And the paper in 2015 showed that for any mu bigger than 0, then which solution eventually becomes smooth solution in 3-dimensional case. And this result is the only result so far in this direction. So the one question we can ask is, can we construct block solution or show that solution are bounded for any mu bigger than 0 and n bigger or equal to 4? So this question is widely open. Right. So, but the minus mu U square here is the minus mu U square optimal in revenge follow-up, in the sense that if it's smaller than this, then a solution follow-up. If it's bigger than this, and solution exists globally. And in 2017, we have the answer for that. CM showed that it's not optimal. Actually, we can make it better. We can replace that minus mu U square by this term we call the sub-logistic degradation term. So we divide it by log to the power p, where p belongs to 0 to 1 and tau equal to 1. He proved that paper. And then 1 year later, he improved that for, actually not improved, but proved for the parabolic system, elliptic system, when tau equal to 0, but p equals to 1. So, so even for the case p equal to 1 and tau bigger than 0, it's still open. So do solution exist globally, or we can construct block solution in that case. Right. So we call this is a sub-logistics. Right. So this is the result in 2017. Now we go to some block-up result. For example, we consider the sub-logistic source for k belong to 1 and 2 in general. And the first result was in 2011, Wigler constructed block solution in high dimension, specifically n bigger or equal to 5, and k less than this certain number. But the second equation he considered is not the equation minus Laplacian of v minus v plus u, but instead we have mt, where m is the average of u. And 7 years later, he improved that work for in low dimension. For example, n equal to 3, k less than 7/6, and k less than this certain number for n bigger or equal to 4. But the second equation is just the normal elliptic equation, minus Laplacian of v minus v plus u. So those are the results for blow up for logistic source. So it do exist, right? It does exist. For k less than 7/6, right? So the gap between 7/6 to 2 is still open. Whether if for example, in three-dimensional case, k bigger than 7/6 and less than 2, can we show that solution is bounded, or we can construct block solution is still open. Right. Now we return to two-dimensional case. We consider a general degenerate drought diffusion system. So reversely, we consider dV just 1 and SV equal to 1. But now we consider general functions for D belong to C2 and S belong to C2 intersect with W1 infinity. So this assumption is quite strong because it requires the derivative is bounded and its function is bounded. So if we can remove this condition, then it would be nice. Yeah. And here the second equation, we consider tau equal to 0 or tau bigger than 0. So we call the degenerate, non-degenerate case if the infimum of D is positive. And this one can be handled by variation method in subleft spaces. And for the degenerate case, when infimum of D equals 0, then it requires new tool. And that tool was founded in 2022. So look at the equation. For example, we have ut equal vt equal to Laplacian of v minus v plus u. So if u is some kind of something like this, then we have some certain control for v, right? So that is the idea. But in this case, we have some double integral, something like this, some estimates like this. Then v is bounded. V is bounded at all time. So that heuristically the idea of the result in 2022. So he can show that the logistic charge RU minus BU square is actually strong enough to prevent block, and the tool he used the parabolic regularity in Euclid spaces, right? And so we can ask the question. We can combine the paper in 2017, where Fu equal to this, the sub-logistic source, and the general equation like the paper in 2022. Can we show that solution exists globally or blow up? And we found that our main result found that when P bigger equal to 0 and less than 1 for non-degenerate case, and P less than half for degenerate case, then solution exists globally. So the question is, can we construct a finite time block solution in the counterpart? Yeah. And as you can see from the degenerate case, then P less than half. So why is it? I will explain that later. All right. So before going to the main the proof, then let me recall some local existence results. The definition of local existence, local solution is that UV belongs to this space, and T max we define as a maximum existence time. It can be infinity, and we have one nice property in the equation too. So when T max is less than infinity, then we can show that UL infinity norm and VW1Q norm converted to infinity as T max converted to T converted to T max. So in other words, if this is bounded at all time for all T belong to 0 to T max, then we can imply T max is equal to infinity. Right? So that strategy can be applied to obtain L infinity norm, L infinity bound. So we can show that this one is uniform bounded in time, then T max automatically equal to infinity, and we have global existence of the solution. Right. So this is not the first paper to prove the global existence. There are many different papers in the past come from after the 1970s, but this is I just borrow this theorem for convenience. Right. So some known result in the past. If you are interested in investigating local existence, you can see the paper of Yaki in 1997. On 2005, they adopted and modified the method 1997 for general quasi-linear chemotaxis system, and the paper in 2011 by Wingler proved the global existence of for solution with general logistic sources. And the idea is you extract the solution by using his semigroup and estimation LQ estimate for semigroup, and then you fix point argument to obtain the local resistance result. Right. And now we return to our main result. So let me recall the general equation. Here we have D belongs to this space and S belongs to this space. However, we have to assume derivative of S non-negative. So this is the differences between the paper 2022 and our equation. So our problem requires extra one condition, S is non-negative. Sorry, F prime is non-negative. Right. Okay, and however, we can replace that by sub-logistic source. We can replace by this term. Right. And the initial data has the same condition. V0 belongs to W1 infinity. And those are non-negative functions. Right, so we have the main theorem. Theorem 1 is for non-degenerate case. For P is less than 1 and the infimum of P is positive, then the system here possesses a unique global boundedness solution, in the sense that this one is bounded and T max equal to infinity. So I forget to add it there. So this can be handled by variation method in superlative spaces. We will talk about that later. And for the generous theorem, then we have P less than half, and if we less than equals is equal to 0, then we do have this bound also. Right. Okay, so now let's go to the sketch of the roof. So this is a different thing. So I will talk about that if we have time left. Right. So the strategy and the tool, first of all, talk about the strategy. How do we prove that? We can divide it into 3 steps. For step 1, we will find some function G such that it satisfies some slow roll condition. For example, G can be U log U or something like that. And the interval here is bounded at all times. So in the past, people always I haven't seen any other paper to choose G. They just consider G is U log U, the entropy. But we actually, when we look at a lot of research paper, we can find a uniform method, which is this one. So we found that if we consider a function G satisfy the slow roll condition, then it works like this. So we don't have to use U log U. We can use something like U log U to the power k, and it suffices to avoid blow up. So this is the new idea, the only new idea that we obtain compared to other results. The strategy here is common in many chemotaxis papers, but this is something new. So, right, and after having step 1, then step 2 becomes common in treating blow up or in treating global existence of the solution for chemotaxis. We will find some constant P bigger than 1, so that the LP norm here is bounded at all time. And finally, we can establish some inverse order inequality to proceed the Moser iteration procedure to obtain infinity bounds. Right. So the difficulty is, can we find some function G satisfying this condition? right? And the tools, we just use some simple inequality like Ron wall inequality and some variation of Galileo-Nuremberg interpolation inequality. So I mean, variation, we have something stronger than Galileo-Nuremberg inequality in some sense, right? We'll talk about that later. And also we need some elementary inequality, Young inequality with epsilon and so on. But I forget to mention, we do have to use the regularity for Oakley's regularity for parabolic equation and Sobolev regularity for parabolic equation, right? But those results, we just apply some theorem. We don't use it in the main proof, so that's why I don't mention here. I just use the theorem. So I don't go into the technique of those, so I didn't list here. Right, so now we go to the main proof. Right, so as in the strategy, we have to find some function g, and here we have so to this is I just simplify the method for elliptic case, but for parabolic case we do have to mention the radiant term for v. Right. So the idea is to find a function g so that we can satisfy the following property. If we differentiate y, we have two terms, I and j. I is coming from the first equation and j coming from the second equation. The second equation is easier because it's just a linear equation. The first equation contains a nonlinear term. And I here we can separate it by IG and IB. IG standing for the good term and IB is the bad term. IG is non-negative, non-positive. And similarly, we have for G. And the idea is that we obtain the following inequality. The bad term can be controlled by the good term, but we have to pay with the cos C epsilon here. And JB is easier because it's just a linear equation, then we can easily obtain this. But the first estimate is the most difficult one. So how do we find appropriate function g, and how do we divide this estimates? So we find these, then we have this following inequality, and we just nicely use Ron wall to obtain the L infinity for y. So that is essentially the idea. All right, so now we go into the detail, the sketch of the roof. So it turns out that the function of g is this this one. We will show that this one is bounded, and we also show that this double integral is bounded at all times. So we will find instead, normally in chemotaxis they just consider k equal to 1. They don't consider k equal to other constant. And I didn't understand why, because in the past they used diffunctional a lot because it's related to the equation, and but we do have some room for k, so I just realized that, and this is something interesting, so I try to do some computation, and it works. Right? So if we consider k here, then we just apply the strategy we discussed at the beginning before. So we differentiate y, and we have some I plus j in here. I already compute I and j for you. So Ig is a good term. We just need minus mu u square here, log k minus p, and jz is this term. And the bad term is this. Turns out after computation, then we have IB is this term and JB is this term. We have some similar terms with this, where the function phi1 is defined as this integral and is bounded by this one. So that's all we need. So we can handle IB by using iteration by parts. Iteration by part, we can rewrite the integral here as this. So that's why we need the non-negativity of f prime. So we can cancel the second term. And then for this, we just apply Young inequality. We separated this is JZ, a good term, minus JZ, I'm sorry. So this is minus JZ, and the phi1 here is bounded by, before we bounded by Z log K minus 1 Z plus E. So square it, then you have this. And finally, we just use some elementary inequality to obtain the last inequality. So remember, so we pay attention to the last inequality. We do require 2k minus 2 less than k minus p. Right. So if the power here is smaller than the power, then we can choose any for any epsilon. We can choose C epsilon here, such that is satisfied this following inequality. So because of this inequality, then we have k less than 2 minus p. So we require k less than 2 minus p for that reason. And later on, then we show so this is the difficult part. So that's why I show the argument here. But for the second term, the JB, the back term, because it's quite straightforward, then I just write out the result. Okay. But from the second equation, then we see k bigger than p. So all in all, then we have k bigger than p and less than 2 minus p. So from that one, then we have 2p less than 2 and p less than 1. So as you can see from non-degenerate case, and we require p is greater than 1 to have the estimates. Right. So then we finish the estimate for step 1, and then we go to step 2, the LP estimate. So in the LP estimate, and we do need some version of Galileo-Nirenberg inequality. We call GEL. L is for log, because, for example, in here, if we consider Q equal to 2, so let's say Q equal to 2, and this one becomes U to the power 3 less than. So by Galileo-Nirenberg inequality, we do have some CGN, integral of radian of U square, and times radian of U, and plus some integral of U to the power 3. See, right? So this is in two-dimensional case. So we have something like this. But if this term is bounded, then we have some constant times CGN times the integral of radian of U square. Right. So if this constant is sufficiently small, then we can absorb into the diffusion term. But we cannot make it small. We have to have some way to overcome that situation. But because of the initial estimate, right, we can replace U here by U log U. Then we have the free to choose epsilon. Right. So if we have something better than L1, we can pay back with the epsilon. So epsilon can be chosen, and then this one is bounded. Then we can nicely overcome that situation difficulty. Right. So now we go to the detail. So it's the same as in the strategy of we use variation. We define the functional here, and we differentiate, and we have IG plus IB. Similarly, we can from the initial estimate, we can separate it into I good term by bad term, and here I good term I already computed. So pay attention to this. So if for non-degenerate case, then we have this one. Non-degenerate case, then D is bounded from below. We have this inequality, but for degenerate case, infimum of D can be negative, can be 0. And this we don't have any control for that. Right. So that one makes the problem for non-degenerate case become more difficult. Right. So we computed IG and IJZ here. And the bad term is, it turns out that we have to control u to the power q and radian v square and u square radian of v to the power 2q minus 2. And we just apply Young inequality. So we have some epsilon here and C epsilon here, right? So for this term, we can just use Galileo-Rydberg inequality to obtain what we will need, because we have epsilon here, right? So we can multiply by epsilon, so we can control the size of radian of u of v. But for this term, if we apply the Galileo-Rydberg inequality, then it's failed because the C epsilon here is big when epsilon is small. So we have to use the adaptation of Galileo-Rydberg inequality that I discussed at the I discussed before. So so it turns out we can replace by the function gu by log u. So if we use that, we already have this, right? So if we use that, then this one is less than C epsilon, and we can choose epsilon sufficiently small, and we have the essence, right? So so now, so this is for estimation, LQ estimation for degenerate, non-degenerate case. For degenerate case, then we need the following theorem. So we need the estimate the English regularity in parabolic equations. So we consider the following proposition: for the parabolic equation, if f is satisfy this condition, double integral less than k, then solution V is bounded. And how do we prove that? So this is a long proof in 2000, the paper in 2022. So I just use the result without touching the proof. So we just admit that here. So now we return to our problem. So remember that we have u log u to the power k estimate for non-degenerate case, and we do have this estimation for degenerate case. So if we have this estimation, then combined with the previous proposition, then we can show that V globally bounded. Okay, so then because V is globally bounded and D is continuous, then we can eliminate the degeneracy of the diffusion term, because now V is bounded. It cannot go to infinity. So infimum of D must be positive. So if we do this way, then we don't have to deal with the degeneracy. We can show V is bounded first, and then it cancel eliminate the degeneracy. Right. So now we go to the Moser iteration. So this one was first found by Aki-Kost. We call Aki-Kost Moser iteration for the diffusion equation, and it appears in some textbook, for example, in superlinear parabolic equation, and also in many papers in Chemotaxis. So here I just recover the idea. We will discuss about the idea. So if we so for the elliptic equation, then we remember when we studied the Cauchy method, we have some radian now delta u equal to f. Then for LQ estimates, then we have to pay with the smaller ball. But here we consider the heat equation, something like this. So we do have some type of inverse order inequality, in the sense that we define UQ equal to maximum of this quantity, then U2Q can be bounded by UQ, right? For Q sufficiently large. In this case, we consider Q bigger than 2 and in two-dimensional case, right? So we have to find the constant AB and AB are independent of Q, so that it satisfies this inequality. And then we apply the Moser iteration. Right. So we just try to use variation method again and try to establish some inequality like this, and then we apply Moser iteration, Ron-Gold inequality to obtain what we need. Right. So here the bad term, the good term is minus radian of u to the power q over 2. So we can absorb all bad term into this by using elementary inequality. But the dependency of q must be traced carefully. So that is the strategy. And we also do need the regularity for parabolic equation also. So we consider the nonlinear parabolic, the linear parabolic equation here with the homogeneous Newman boundary condition. If f belongs to this space and v is continuous, then if f belongs to L infinity of Lp norm for some p bigger than n, and v belongs to W1 infinity, L infinity of W1 infinity. Right. So now in the detail, we just multiply by u to the power 2q minus 1. We separate by I plus j plus k. I is a good term because the dependency of a constant in q is important. Then I write it down precisely here. And the j is the bad term, the term we need to control. The k term is easy. We don't have to pay attention to k. We need to focus on g also only. But for g, then because we assume u belongs to L infinity of L p norm for some p bigger than n, then that leads to v belongs to W1 infinity. So we can cancel this term easily. And then we apply some Holder inequality with epsilon. Then we can absorb this term into the good term. And this term is just it can be handled by Galileo-Nirenberg inequality. So we can bound the term by u to the power 2q can be bounded by radian u to the power q square times some number, then u to the power q. We have to trace carefully after doing computation, and it works. Right, so we have to choose q as epsilon, and epsilon we can choose after computation. Then we can see that it's just look like a polynomial. It's big O q to the power L for some negative integer L. And then we can proceed the Moser iteration, which is let a sequence of k here. And then we can check that series here is bounded. So we can set k go to infinity, and then we have L infinity. And that completes the loop. Thank you for your attention.
Thank you, Minh, for a very interesting talk.
Thank
So
you.
we have now time for official questions before the informal discussion. So please ask or discuss with me. Okay, while we are waiting, let me ask you. So in the slides, you have some actually quite interesting thing about the boundedness of V. If we solve the parabolic equation, and you have the if f is can you go back a couple of slides? A bit more. Oh, maybe, yeah, this one. This is also, at least it looks quite interesting to me, that if if f square log f to the power alpha is bounded, then you have the boundedness of V. Even
Yes.
this one for parabolic equation, is this new?
Yes, this is new. So I'm aware that some people use maximal functional to do some cat and segment decomposition and prove some result in office spaces for heat equation, but the paper in 2022 used the direct loop of variation method, and that result is new for at least for the homogeneous Newman boundary condition.
Yeah, I think that maybe this one also have some further uses in some other directions. You can, you know, watch out for those.
Yes, thank you.
Sorry, is this 2D or what? Sorry, your result is still, you're in omega 2D, right?
Yes, so so the result here is just for two-dimensional case. Yeah.
And what the conclusion of this proposition? So is that in the
So
next slide?
the conclusion is V is bounded, and the dependency on A, Q, and K and tau. K is the upper bound for the double integral and also initial data.
So can I go back where you need only the condition up to t minus tau, but not up to the condition 20.
Why do I need the condition up to
Yeah,
t?
it looks like that probably we need up to capital T, right? So
He's taking the integral in time into from t to t plus tau.
from T to, oh, this is for all, okay.
Yeah.
So you bump
Yes.
into each of them.
So maybe it would be useful if you can write out this result, this proposition for any dimension, if you have such sort of like similar bounds. I don't know.
Yeah. Yeah, so we do have the version for any dimension, which the slow roll condition for F, but here I just use a part of his result into the paper in 2022. So I just use a part of it. So I just write sufficient for our purposes. But the full result is much stronger.
Thank you. Are there other questions? Okay, so if not, then let's thanks Minh again, and then we will stop the recording and proceed to the informal discussions. Thank you, Minh.
Yeah, thank you.